Hello. Hi guys, good morning. I hope that I am audible and visible. And whosoever is here, can we please quickly have a hi, hello, and for sure, we have Nand. Hi, sir. Cool. We will start off with the first two questions. That's pretty easy. We'll primarily focus on question number 2 and question number 4. Sorry, question number 3 and question number 4. For question number 4, it's exactly same concept as we have already seen before. Binary lifting. If you have not watched it, I'll highly recommend you should have watched it. But if not, then still. See, if you have not watched the binary lifting part, or if you have watched but you have skipped it, there's a high chance the fourth question also you won't be able to understand. The entire logic is same. I'll explain the entire logic again also, but still you should be like, it's a very just like recent contest, so it's a good one. Firstly, hi Gautam, hi Monty, and hi Yash. Great. Just let me know that how many questions you guys solved and all that stuff, and also can you please smash that like baby. We'll quickly jump on to question number 1. So count symmetric integers. Meanwhile, just write down below how many questions you solved in how much time, all that stuff for question number 3, for what you all thought and all that stuff. Just brief me about how you perform the contest. When I say perform, you need to give the timing of the questions, and also okay, and please write in the one statement itself, not multiple lines. That okay. This questions, this much time, and in the question number 3 I tried this, and question number 4 I tried this. Cool. Now count symmetric integers, and yeah, please smash that like baby. Let's say 10 likes, because okay, I know that's afternoon, people are just sleeping right now. It's Sunday, enjoying, but we are here doing contest, right? You and us, you and me. So you are having to two positive integers, low and high. Now again, an integer x consisting of 2 into n digits is symmetric. Again, it is 2 into n digits, which means even number of digits is symmetric if the sum of first n digits and the last n digits are same. Okay. Now I have to return such number of symmetric integers in this range low to high. Now as soon as the range comes in picture, the first thing which should have came in your mind is a digit DP. But considering it's an easy problem, so for sure digit DP would not have come in, and also the constraints pretty well easily can say that I can apply my simple brute force technique, because this would not be required. But again, I am saying as soon as you see okay low to high, we want to find such number of numbers in the range from low to high. First thing which should have come in your mind is a digit DP. If not, then you have not watched any videos of it. Just write digit DP by Aryan Mittal. You will get videos, and that's of contest itself. But that's a problem number 4. Usually it's a hard problem, but yeah, it's an easy one. So for sure I can just brute forcefully go on every number from low to high. Now when I have, let's say, any number, let's say 1 2 0 3, as I'm going on from every number, which means I'll go on linearly on all the numbers from low to high, I'll get a number. I know firstly that number length should be even. Now to solve it, there are multiple ways. One such way is convert this to a string by just a two string operation. Now iterate on the first half and the last half, get the sum, and it should be equal. Or one way is you just iterate on only the first half. While iterating on the first half itself, get the first and the last value, first like last in this value, and keep on basically add this, subtract this, add this, subtract this, and ultimately it should have a 0 as value. Anyway, again, in the last yesterday's contest also, there was kind of a same problem that you need to have the sum, subtract, which means odd and even indexes, places you are adding the locations. Here also I will just want to say ultimately okay, this sum and this sum should be same. So ultimately you can do anything, convert this to a string. Now keep on going on from start to the mid, and keep on adding this and keep on subtracting this. Or you can also say okay, I will just subtract this and add this. Anyway, I just want that okay, ultimately the sum should be 0, and I will just add it and subtract it, and I'll go up to the mid only. And ultimately if this is a 0, which means the left half and the right half sum is actually same. And again, make sure that okay, your length should actually be even, which means no such element should be left in between. And if that's the case, that is actually a good number. So I'll just say okay, if that, I'll go on, and again I'm going on to every number from low to high, so I will just keep on adding okay, if that's a good number, please increase my answer by 1, and I can simply go on increasing my answer. So ultimately I have my answer as the global variable. Now I will go on from low to high. Again, as the constraints were pretty low for low and high, so I can just brute forcefully go on every low and high, right? Now as I have that particular integer, I will convert that to a string. I need to know the sum from the left half and the right half, and that should be equal. So I'll just keep on adding the left half sum and keep on subtracting the right half sum. So I'll go on and have a variable as sum. So I'll go on up to the left halves, and I'll keep on adding the left half and keep on subtracting the right half, and I'll go on up till the end, up till the like half itself, so as to add the left half and subtract the right half, and ultimately as I showed you that okay, my length should actually be even, and also the sum should be 0 ultimately. Only then I have a good that integer. It's a good integer. Ultimately I can return number of such good integers in my answer. Cool. That's for the first question. We'll go on to question number 2, but before that let's have a quick chat read. But before that, can you please smash that like baby to 20 likes. यार, you guys are normal regular ones. यार, तुम्हारी regular शरारतें साथी ना, if you go in a bar, you know, okay, you are a regular one, so I'll treat you differently, right? So that's the reason. Your regular ones, just cheers. आते ही have a cheers at the like button. Okay, like I'll do a cheers, you will do a cheers. As it, right? Cool. Second, using DP is more than 1 hour. 2, sad life. 2, only 3. Great. Hello भैया. Hello Akash. There are a few of them जो मतलब हर बार they are regular. Like I love the spirit. Like you guys are regular. Amazing. Well, I did in the first using a string. It said WA on the hidden test case, but when I did it as numbers only, it passed. Lost 10-15 minutes. It will also work as string. It's just that you have to convert that character into integer only to actually use or basically add them. You can't add characters because a character A has a sky value different, and a character a character 2 has a sky value different. A number 2, so you need to subtract a 0 as a character also to get the actual number 2. So maybe that is a mistake what you would be doing. So that's the thing. I wasted 5-10 minutes just to thought how it would be done using digit DP. No, like for sure, like as I showed you that there are multiple such criteria to understand, okay, if you're gonna apply a digit DP or not. One such criteria is, okay, low to high range, and then other thing is that for sure your low to high range should be big. It should be big enough to apply digit DP. You can't go and apply because it's a hard concept, right? Not everyone knows it. So for sure, and it's an easy problem. So brute force, every time brute force works on it. So on easy ones. Solved second one using recursion. Memo took 2 states indexes previously. Yeah, second one can be done by recursion itself. That's true. Like कर दिया रे भैया. Thank you so much. अबे hey Aryan. Hi Yashwant. अब से regular मैं भी great. अबे yo. Lucky to find your channel. Thank you. Base case index less than 0, return number previous, another if check divisible by 25. That's true. So yeah, that's for the question number 2. Again, it's just recurse. It can be solved by both recursion and maths. Anything which strikes you, although the maths is more intuitive because it's specifically written in the maths form. We will see minimum number of operations to make a special number. Before that, can you please smash that to just 20 likes, just 2 more, just 1 more. It's 19 right now. You are having a 0 indexed string nums representing a non-negative integer. Okay, I have a nums as a string. Now in one operations, you can pick any digit of nums and delete it, which means remove that from the nums itself. And if I can remove all the digits, so I will just ultimately make that as 0. That's also true. So that is also a number, right? If I just remove everything, still I just can know, okay, it will become a 0 if I just remove everything also. Now I have to return the minimum number of operations, which means minimum number of deletions I have to do in my nums as a string, such that the final number formed after deleting elements from nums, it should be divisible by 25. Now if you are not familiar with the divisibility factor, which means that if you are not familiar, so for every number, let's say if I just ask you, if you want to check if a number is divisible by 2, so you would say, okay, the last digit of any number should actually be even, then it will be divisible by 2. Let's say if I ask you for 3, so you will say that the sum of all the digits should be divisible by 3. If I ask you for 5, then you will just say, okay, the last number, it should be a 0 or a 5. Then it's divisible by 5. And same for 25. 25 just says last 2 digits should be divisible by 25, which means it can be a 0 0, it can be a 25, it can be a 75, and that's pretty much it. Or like, yeah, for sure 50 also. So with this, if I have these 4 cases in the end of my string, or basically integer, for sure that number is divisible by 25. So now our main task is to make something like this, right? Something in the end should become like this. Or ultimately I can say that if I have a string nums, now I know that, okay, I need to pick the latest, which means latest as in from the end, I need to pick 2 such integers such that they form this combination, which means ultimately that for, let's say, I just say, okay, as j and I are 2 integers, because ultimately I will be removing some characters in between. Let's say, okay, it is a bigger string, right? Bigger string. Now let's forget it now, okay, right? So let's say it's a bigger string, so ultimately I will be picking up 2 characters, and when I say characters I mean numbers, because it's a string, it's actually a number itself, right? So I'll be picking 2 such characters which can actually form any of such combination. Or ultimately I can just say that j and I ultimately as a number, j and I, when I say number, I can say, okay, it can be a 2, it can be a 5, but as a number it's a 25, right? It can be a 5, it can be a 0. As a number it is 50, right? So as a number 50, it should be divisible by 25. So I just need to pick any of the latest j and I. Now why latest j and I? Because I need to remove some elements. Again I said, I want ultimately that this j and I should be at the end. If it needs to be at the end, which ultimately means I will be removing all of these. Ultimately what will happen is the j and I will come in the end itself. So my task is that, okay, I need to have minimum deletions possible. Again, minimum deletions possible, right? So simply what I can do is I can go in from the back. Okay, I'll go in from the back. I know I have a I. I'm going in from the back itself. Let's say I have this as a string. I'll go in from the back. Okay, I have I. Now for this corresponding I need to find a j. I'll go in and try for every j. Okay, j, and so on and so forth. I'll go and try for every j. Now what I'm trying of is, I'll go and try for this j such that j and I will actually form my last number, ultimately meaning I will be removing these mid ones and my number will be, okay, what is in the left of j plus this j and I as the end digits. Ultimately, and how I will check, I will just say, okay, I have this I at this particular place. I'll go and try for every j. As soon as I find the nearest j possible, nearest j I have met, I have found, great, awesome, nearest j I have found, I will just use that j. So again, you know that there are n characters in this particular string of length n. I have n characters. So before j, how many characters are there? N minus j, right? So I'm saying I will be using these n minus j characters. I'll use this jth character, I'll use this ith character. So ultimately, if I say the length of this is, let's say, n, right, I will be using this n minus j minus of this particular j and I. So j and I, again 2 characters more. So nothing but you will not be removing these 2 also, right? So you will not remove these 2 also. Again, you will not remove these 2 also. So n, it is n, I'll show you, 0 1 2 3 4 5 6 7, length is 8. So 8 minus 4 characters I am not removing. I am not removing my j, I am not removing my I, I am only removing these middle ones, right? So that is, I can say, okay, I'll remove out of my total, let's say the length is n, right? I will be not removing this n minus j, and I will also not be removing these ones, which is these two ones I will not be removing at all. If I'm not removing these at all, I would know for sure that number of characters which I would be removing is actually these 2 itself, which is 4 will come from here. So n is actually 8. 8 minus 4. 4 remaining, minus 2. Okay, minus 2 is for this j and I, again 2 remaining. So these two I would be removing from my actual string of length n. This is how you can just simply go and try for the latest I and j. That, and again for I and j, I will just get a j value at j. It will be nothing but j into 10. J, I actually mean the value at j, which is nums of j into 10 plus nums of I. It is the value, because ultimately my main task is I will be removing every characters between j and I, and also as my I will move, let's say my I moved here, because let's say I could not find any j and I combinations such that it is divisible by 25. So again, my I will try for the next location. It will again keep on moving. My j will again keep on moving left. So again, you know that, okay, my j and I should come in the end, right? So everything between j and I will remove, and everything after I will also remove. So ultimately, you know that every character which is before j, all this which is n minus j, it will come, and also j and I will come. So the number of which you will remove is remaining out of n minus j, and these two characters you will remove. And that's how you can just simply go and try for all the n. For sure, you can just have a O of n square algorithm, because you will try for every I. For I, you will try for a j. So it's a O of n square algorithm, which you can just try off. And with this n square one, you can just say, okay, I am good. You can just simply take this down, and if that number is divisible by 25, so that's a good number. So I will be removing these characters in between, and that I'll just try to minimize that, and we'll get the answer. It's just that a small case in this, that you know that, okay, right now I'm picking up pairs for sure, which means I am having a I here, I am having a j for sure, right? So I'm just assuming, okay, I'll pick up a pair, because as I started 0, 0, 25, 75, 50. Now, if I ask you if I have only 1 0, it's also good, right? 1 0 is also okay. 0 0 and 1 0, okay, 0 0 in the end, it should be there. But what if I say, okay, I have only 0 as my final value remaining? I have only 0 as the final value remaining. I'm not saying I have 0 0 in the end. I'm saying, okay, I have only 0. So what I'll do, I'll remove everything from left and right. So that's also valid. It's 0 is divisible by 25. So that's also one case which you can handle, because 0 as a value, ultimately it's just a one number. It's not a pair. I and j, it's not there. So you can just assume, okay, I have a value 0, and that for sure 0, it needs to be handled differently. If I have just a 0, for sure, I can just remove everything other than it. I'll simply get a 0, and it is multiplied by 25. I can simply get the answer. With this, you can simply get what is the minimum value, and you can keep trying on for that value. Now we will see the code, but then I think that, okay, if it is a bit more mathematical and a bit more conditions for you, then there's a much more easier way by using recursion and memorization. How? Simply at this particular locations, what we are doing, we are deleting a particular character or a particular number or a alphabet, you can say. I'm deleting that particular character itself in my string. Now I just want to do the minimum number of deletions, right? So it's just that, okay, I have a string with me. I will just ask, shall I delete it? Shall I not? Shall I delete it? Shall I not? Shall I have it? Shall I not? So it's just that, okay, I can also apply DP in this. But again, more intuitive is actually mathematical approach, because straightforward they are projecting you in the mathematical direction. Still, you can solve it by DP. We'll see DP also, no worries. But yeah, let's quickly have a look at the mathematical part, that I will be having I, and then I will be iterating on the j backwards. Again, for I also I'll be iterating backwards, and then I will just find the answer. Cool. Again, as we showed above, we will be having our simple, I'll move my I backwards, I'll move my j backwards from the I itself, which means j is I minus 1, and then moving backwards. Now I will just get the last number with, and that will be nothing but, I assume my j and I value are the last values. So it will be nums of j into 10 plus nums of I. So it is nums of j into 10, nums of j into 10 plus nums of I. That's the last number which will be formed. Now, if this number is divisible by 25, it's a good chance to actually have this j and I can just delete everything between this j and I and after I, and I can only have everything before j. Now if the index of 1 2 3 4, if the index of j is actually 4, so you just say okay, I have j positions here, I have these 2 also here, so out of this n I will just remove, I will be just using this j and these 2, rest all these 2 and rest all I will delete. So out of this n I will use j and 2, rest all I have to delete. So I just want to know how much I have to delete. So I will just say this n minus j minus 2, n minus j minus 2 I will actually delete from my actual betweens, which means after I and between j and I, and everything before j I will take it, and what is the number of that? It is nothing but n, it's nothing but j. Cool. With that I will just keep on bringing my answer, and I want a minimum answer possible. Again, as we saw, there's one condition, what if I have only 1 0? So if I have only 1 0 also, that also ultimately the number can be formed as a single 0, and that 0 is divisible by 25. So for sure answer will be n minus 1, which means okay, I will just delete everything apart from that 0. So I will just have ultimately forming as 0 because I just have n minus 1 deletions, and ultimately I just got the answer. So with this you can just try on every possibility having j and I, and we'll get the minimum answer possible. Again, as we saw above, we can also have take and not take as an operation, but before that, if the folks have understood the first logic, can you please smash that like baby to 25 likes, just 3 more, that would be super great. Again, for this operation we can have a pick and not pick or take and not take operation, just saying okay, I have all these particular values, ultimately I just want that my number formed in the end should actually be divisible by 25, so I can just simply keep on forming my number. And as we know, in a recursion we will be going on to every index, but as we go on to every index we also need to maintain what is the current number, right? Because ultimately I just want that ultimate number modulo 25, or I can also say I'll just maintain the current number modulo 25 also. So I'll just go on to every index. Let's say I am at this index, okay, I'm at this index, I'm at this, which means it can happen, okay, I did not take this, I take this. Now let's say I'm planning to take this also. So what I will do is whatsoever number I have got so far, okay, that number I've got so far into 10, plus if I'm taking this number, I'll just add this number again, I'll do a mod 25 because ultimately I'm only concerned about the value mod 25 and it should be ultimately 0, right? So I'll just simply make sure, okay, if I'm grabbing a number, existing number, I will just pass in my argument, okay, existing number is 0. Initially in the beginning, existing number is 0. As I am making on the number, okay, it becomes a number, let's say nums, or let's say n into 10, because for sure I am putting up the value in the end, n into 10 plus that current number, let's say it is as n2, or let's say I, it's a number, it's not an index but it's a number, right? Let's say nums of I, and again mod 25 I will pass on to the next argument. Again when it will land on to this value, again I can have an option take, not take, take, not take. Ultimately again in the end it will ask me, okay, take, not take. If I take it, I will just do, okay, what's the last value? It will give me the next, it will give this value as an argument to the next recursion call. If it is a last value, I will just have, okay, it is n into 10. If I take it, if I take this value, so let's say value is 2, so I'll add a 2, mod 25. If I don't take it, so I'll simply pass this n to the next function call and I can simply increase my index also. It's just a simple recursion going on forward, just taking the value and not taking the value. Ultimately concerned of key that number being formed should be modulo 25, or I can also say that I will keep on maintaining the modulo 25 also. Just simply we want the index and we also want the number as well. And that's number is actually number modulo 25 because I'm only concerned about number modulo 25. Ultimately, I just check, okay, if this number modulo 25 is actually a 0 or not, and I'm only passing in number modulo 25 modulo, so it is always less than 25. That's the reason my argument, it never increased a lot. If you will pass in the number, then your recursion will give you a TLE or will give you a MLE. So you need to know, okay, the indexes are just 100, and also the you are passing in number mod 25, so it will be less than 25. So that with that you can just simply go in the recursion. For sure the base case is, as you have reached the end of the string, just check if the number modulo 25 is actually a 0. So for sure nothing more you want to delete, you are good. But if it is not module 25, so whatsoever you did, the deletions was not good, and the ultimate string formed ultimately with you is not module 25, but you want it only module 25. So please give a very higher value, because I want the minimum number of deletions to actually form a number which is module 25 itself. And now it's a simple recursive memoization stuff. Now as we go on to the actual recursive case, I will have a not pick and pick condition. Now not pick is nothing but I will not pick this particular character, or basically this alphabet. If I will not pick it, which means ultimately I'm saying in my mind, if I'm not picking it, which means I will delete this. So as I'll just add a 1, because I will be deleting this as I'm not picking it. Now if I will not pick it, so I'll just delete it, so I'll just add a +1 for it, and I'll go on to the next index, and also the nums will remain same because I did not modify my nums. Again, if I pick it, then what will happen is I'll go on to the next index for sure, but the nums will now be modified by saying existing nums plus the current digit what I got into, or like again mod 25, because I am ultimately concerned that the value should be remain under 25, ultimately passing the s as it is. So whatsoever I will get the value from pick and not pick, minimum possible value, just pick that minimum possible value, ultimately assigned to a DP, and that's how you can simply get this done by DP also. Again, for this both you can apply. For me, the more intuitive part was using this, but it is a bit tricky to implement and also a bit harder to actually see the HKSN stuff. It is not that intuitive to implement the DP one, but it is much more easy and straightforward, because we have seen and done many such problems previously also. So it was very easy and very straightforward. Okay, for sure, no edge cases, nothing at all, just a straightforward answer, and it should be very easy. But again, it is not intuitive to actually think of DP in the first place, because math will come in the first place for sure, because as soon as you will read this word divisibility, you will start thinking about the divisibility factor of 25. Cool. We'll quickly jump on to question number 3. But before that, can we please smash that like baby to 30 likes? Just that would be super great. Just 3 more, that would be super great. We will have it done. Just having a quick chat read. We'll just after that we'll quickly go on to question number 3 and then 4, because 3 would take a bit time. 4 will also might take a bit time, but it should not if you have previously watched. But like, firstly, comment down below that who all have watched the binary lifting video and have understood it from the last contest. Just comment down below quickly that who all have watched that binary lifting video, so that I would be knowing. Okay, and see, okay, just comment down below who all have not watched the binary lifting video from the last contest, in which I explained the binary lifting entirely. If you have not watched it, please, I highly recommend just go and watch at least, and at least have the notes being made. Cool. Hey, ab se regular yo. I am watching your videos for more than 4 months. Great. भैया 4 करवाओ, अभी आ रहे हैं 4 पे. Wow, now I get it. Love. We also can do it linearly for 2 questions, right? Didn't get why you did modulo 5 for nums, because if we did not do modulo 5, then the sum will increase a lot. As you will know that you are actually doing what? You are simply, you are just doing the number of this length, the number of length 100. It can increase, right? A lot. So see, the maximum number of length 18 you can form, not bigger than that. So you just need to maintain the length of the number, as it will just go MLE, TLE, everything it will go out, right? Cool. We'll quickly go into question number 3. Again, question number 3 was actually a standard problem, but a bit bigger, which means it is just implementation of 2 standard problems side by side. That's the reason I always say, when you are actually solving a problem, just break the problem down and then solve the problem, not just solve the problem entirely. What I mean by that is, I'll tell you, but just break the problem down. What I mean by that is count interesting subarrays. Before that, okay, let's skip the ads. We don't want ads. Cool. We'll go on to question number 3. Before that, can you please smash it to 25. Cool. Count interesting subarrays. You are given a zero index integer array called as nums and an integer modulo and an integer k. Now, okay, I have a array nums, modulo and a k. Now I will name this modulo as m. Remember this, I will name the modulo as m because when I will say a number modulo m, I actually mean modulo. I can't speak, okay, a number I modulo. That's very abrupt. So I'll just use I modulo m, which means a number modulo m. When I say m modulo, I actually mean by this modulo itself. Remember this fact. Cool. And an integer k. Now my task is to find the count of subarrays that are interesting. Again, I'm interested in the subarrays count. Cool. That's again a big hint. You will see how. Basically now it says, okay, how that subarray L2R is interesting. It is interesting when the count I'll just explain you what it means is that firstly, I just want the number of numbers, all such numbers, which means if I have a subarray in which my nums of I mod m, if it is k, then that's a good number for me. Okay, I will just mark, okay, it's a good number, and again, and how I say, okay, it's a good number is that nums of I mod m is actually a k, then it's a good number for me. But ultimately I want that, okay, the count of such good numbers in my subarray mod m should also be k, which means that, okay, the count is actually 2 now of this number of good numbers in this subarray. So this count of this number of good numbers, which actually 2, mod m should actually also be k. Now again, it's a condition on top of another condition. That's what make it a bit tricky, but still we will assume it as one step and then next step. We'll not go in directly. We'll assume, okay, I have never ever watched this condition. I will just assume I want to find the number of such subarrays such that nums of I mod m, if it is equal to k, and I will find the answer in respect to that only. How? Let's see. What we will do is, okay, return the integer noting the count of interesting subarrays. Again, I am saying for me right now the interesting subarrays, I have said, okay, it is all such subarrays such that nums of I mod m, it should be equal to k in that particular subarray. Cool. Now a subarray is just showing, okay, it's a continuous array part. So my prime aim is, forget this part. Again, I'm saying forget this part. My prime aim is to count the number of such subarrays such that nums of I mod m should be equal to k. What all such subarrays are there such that nums of I mod m is equal to k? If it is there, then I can just simply go and say what all are the subarrays for me. How I will do it? Ultimately, firstly, again, going a step back, I want nums of I mod m should be equal to k. So firstly, what all such numbers that are good itself, and then I can just maybe find the subarray, right? That, okay, I just want such number of subarrays that has the condition like this, which means now, for example, for this particular case, when I ask you, okay, it is one such a subarray. Let's say if I have a good here, because for sure if a good is here, so I want exactly one such element. I'm not saying I want count mod m such element. I just want one such element which is good. I want just one such element which is good. And how I define a good? I just define a good. Good is nothing but in my entire subarray, I just want one such element to be good. That's it. That's what I want. Now, if that's what I want, I can just simply go on and say, if I have a particular array in which, firstly, I will just mark, okay, all these elements are good, good, good. If I have not marked an element, which means it is not good at all. Now, again, if I ask you, if I want that I need to have good elements in my subarray, so, and it needs to have good elements, as in I can just have this subarray, it will have good elements, or basically it's saying the number of good elements for me. Let's say if it is good, so I'll just mark it as a 1, 1, 1. Now I want to ask you, hey bro, if that sub array is actually good or not. If that sub array is good, so I can easily say, okay, I want that, okay, this is a sub array which is good, because it has, I started from here itself, and I can go on to the last good one, and I can say, okay, it is one such good sub array, it is one such good sub array. Again, there are many, there can be many, but I'm just saying, okay, it is one such good sub array. Now, when we have broken down, still we're just confused that we just are right now concerned only on the point that nums of I mod m should be k, but nums of I mod m should be k, we have already got these values. Now these are all the values which are nums of I mod m as k. Now we're concerned about their count. Now if I'm concerned about the count, how can I know the count of such number of good elements itself? Now I just want, I just now my main task is to find the count of such good sub arrays. Now for the count, I might need, okay, I might need the number of such good elements in that particular range, right? Okay, Aryan, now I want the count of, again, the count of good elements in a range. I want the count of good elements in a range, which means ultimately, if I just go and ask you, hey bro, can you just let me know what is the count of good elements in this range? So you should be able to tell me, which means I will just ask you, okay, I'm standing here, I want to know the count of good elements in this range. Let's say if I ask you, what is the count of good elements in this range? What if I ask you, what is the count of good elements in this range? So now your task reduced to, you want to find the count of good elements in a specific range or in a specific subarray, because that can be a range. So what I can do is, I know, okay, if I want to find the counts of some specific numbers in a range, I can just use the prefix sum technique. And how that can be used, again, I'll just modify it a little bit so as to make the example much bigger. I can just put a 1 also here. Now putting a 1 just indicating is, okay, that is a good element. Now again, to define a good element, I'm saying that the nums of I mod m should be actually a k. If that is a k, then that's a good element. For a good element, I'm just placing a 1. Cool. I'm done with it. But now my task is to find the good elements in a range. So what I can just do is, I can just maintain the prefix sum. Now if you had not known this technique, it can just let you know the number of such elements what you require in some specific range. How? Let's see. Now for sure the prefix sum starts with the value 0, although it's not visible, but it starts with the value 0. Then okay, now why start with the value 0? Because what if I had 1 also in the beginning, which means 1 is also a good element. So again, I'll just ask you, because prefix sum, as I was saying, prefix, I'll go from the left to right, prefix, I'll go and I keep on adding that element. So I'll just get, okay, it's a prefix sum. I got another one, so a 2 came in. I got another one, so 3 came in. 3 came in because it's a 0, which means nothing is there, just simply a 0. Okay, a 1 came in, so 4. Again, 4 will actually happen here. Now 5. Now again, it's a 5 itself. Now, if I just go and ask you, hey bro, what is the count of good elements in this range? So you will just say, okay, I will just get the value this because I want this range, and as I'm ending here, so I'll get the value this just before this. So with this 5 and 2, I know, okay, I'll do a subtraction of 5 minus 2, I'll get a 3, which actually indicates me I have 3 good elements in this range. And how that happened is, you are just summing up, you're just adding up these ones as you go on from left to right. So this 3 is having this one, and this one. So it is having, let's name it A, B, C, D, E. So this 3 is having A, B and C. This 5 is having a B, C, D and E. This 2 is having a and B only. Now what I ultimately wanted was C, D and E. So I will do a B, C, D, E minus A, B. So I'll get a C, D and E. And that's how I'll get a C, D and E. So with this prefix sum technique, you will be able to find the count of such good numbers in a range. Right. Okay. Now my half of the task is kind of done, that I will be able to get the count of such numbers in my range. I will be able to get the count of such numbers, but I'm not concerned only about the count. I also want that the count modulo value I'm concerned about. Okay. I can get the count with this. I can get the count with this of any range, which means it will just help me. Okay, I have the prefix value, I have the prefix value. It will just help me to get the count of that range. But I'm not concerned about the count. I'm concerned about the count modulo m. Okay, so I need to do the modulo of this entire array, because ultimately I will be doing a subtraction and ultimately doing a modulo also. So I will be doing this. Let's say if I want to find, okay, from this range to range, what's the count? So I know, okay, for this range to this range, the count, that's xyz. So for that, I need to know that modulo also. So I will also have to do a modulo. So let's say the modulo value is, let's say 3 here in this case. So, right, the mod value is 3. So we also got to know, okay, I have to find the count. That is one factor for me, which I can do it by using a prefix sums, but also a modulo is coming in picture. So for sure, one thing is what I have to do is, while I will be finding the range, I also would be doing the modulo itself. So as the modulo operation comes in picture, we know one thing for sure, that if I do a subtraction, so this minus this, and it needs to be mod m. So I can also say, okay, as you know, it is increasing, but still you have to do a modulo of that value. So I can just simply do a modulo at this point also. Let me make it straight. If it is straight, 1 1 2 3 modulo 3. Again, I'm just doing okay, this is the array which I made as a prefix array to get the count in a range, because I was concerned about the count, but I'm also now concerned about the modulo also, because I will be doing a modulo also at this step. So either you can straightforward use this also, but if you use this, then maybe in future you can you might be able to apply things or not. But meanwhile, like, we're just trying out right now, so we are just using, okay, let's try do a prefix modulo m. So I'm just doing a modulo m. My m is actually a 3. Okay, cool. 3 mod 3 is actually a 0, 3 mod 3 is 0, 4 mod 3 is 1, 1, 2 and 2. Now, great. Now again, if I ask you, hey bro, can you just give me the count modulo m in this range? So you can just say, okay, simply here it is a value 2, here it's a value 2. Right, so nothing but 2 minus 2, 2 minus 2. Again, when you do a subtraction, please add modulo also, which means please add m also by doing a mod m, which is a standard concept of modulo, that a minus b mod m. If you are doing a minus b, always make sure that you do a minus b plus m mod m, because b can be large, a can be small, so this can become a negative. If it is negative mod m, it will give a wrong value. So please do a plus m while doing modulo. So that's a standard concept of modulo that you do while doing a subtraction. But now you can easily find out count mod m. Okay, it's a 0 plus m mod m is actually again a 0. So again, the count of the good numbers was 3 in this range. Now 3 mod 3 is actually a 0. So that's good. But what if I ask you, what is the count of such good numbers in this range? But I am concerned about the count modulo m. So I just ask you, hey bro, this is this number, this is this number. So 2 minus 0 plus m mod m. 2 minus 0 plus m mod m is actually nothing but 2 plus 3 mod 3 is actually nothing but a 2, which is true, because I have 2 good numbers in this range, and that's nothing but it's not 2, it's actually count of numbers mod m. Now ultimately, this is what I'm doing in the left side, which means I am just right now saying purposely, I am trying to find a range where the count is this. But ultimately, I'm concerned about all such ranges where such count is actually k, which means right now I was saying, Aryan, can you just find and let me know for this range what is count mod m. But what is count mod m? Because ultimately I'm concerned, okay, what is count mod m? Okay, if the count mod m is xyz, and if this xyz is actually k, so it's a good range for me. So ultimately I'm concerned about a good range for me. So rather than now saying find the count mod m for this range, I will just ask you, I know that okay, my count mod m should be equal to k. So I know I am ending at this I. Can you give me all such ranges starting from I such that the count mod m is k? So which means that okay, we have maintained a prefix sum. Now let's for our simplicity, we have made this count mod m kind of a array, which means prefix mod m we have made it for us. Now ultimately I want that my k you can assume is anything for now. Let's assume your k, what was your k? K, let's say k was the number of such integers which you have, right? It was the count of such numbers modulo k. So k is nothing but a number. So let's say the k is actually 2 for us right now in this case. So if I'm standing at a location, I want all such numbers. Okay, I'm standing at this location right now. I'm standing here. Now this value indicates what this value indicates. It indicates prefix, let's say end, prefix end mod m. It indicates this value. Now ultimately what I want is, I would want some location. Again, it's a question mark. I want some location, and when I say some, I mean all such locations. Prefix of 1 mod m I want such that, and prefix of, let's say here is a 2. So why I want such that prefix of 2 mod m, and it's a mod m value, so basically it's a value of this particular array, minus this prefix of 1 mod m, this mod m, because this will give me the count, right? This will give me the count. It should actually be equal to k. That's what I want. K count mod m should actually be equal to k. That's the condition for me, right? Count mod m should actually be equal to k. So, but here I know, okay, I'm standing at this index which is prefix 2 mod m. I want to find all such prefix of 1s. So rather, just move this thing on the right side, bring the k on the left side, because k is something what you know. You are standing at, you want to find all such prefix of 1s mod m. So what I'll do, prefix of like prefix 2 is nothing but this particular value, mod m is this value, minus k, nothing but minus k, and if you do a minus k, please make sure okay you are doing a plus m mod m. It should actually be equal to my prefix of 1 mod m. Ultimately saying that okay, if you had a 2, which is actually this value. Now you will do a minus k, again minus k you will do, and k for sure for us is actually a 2. So okay, you will do a minus 2, which you will just get as a minus 2. So minus 2, and it's a 2, which actually a 0 plus m. It's actually again 3 mod 3. So nothing but I will get a simple 0. Ultimately, all such prefix of 1 mod m which are actually 0 will give me the correct answer. So I can easily say, bro, this range is a good range for me. This range is a good range for me. Why good range? Because this range will make sure the prefix of 2 mod m minus this prefix of 1 mod m, because prefix of 1 mod m is actually a 0. So this value 2 minus 0 mod 3 will actually again be a 2, and I wanted that part only. So ultimately you saw, I just now want all such prefix of 1 mod m which are actually equal to this, and this is, I know I am standing at this I location, so I know this prefix of 2 mod m. I know the k for sure very well. I know the m for sure, so I can just simply go and find all such prefix of 1 mod m. So right now I'm standing at this. I know by the logic which I have, I want to find the 0, all such zeros whatsoever are there. If I know okay, number of such zeros present in this particular array, which is the prefix array which I have made, 2 and 1 are just the name which I have given at for the specific points. But if I know this entire array right now, I can just be very sure okay, at this location right now, if I can just go and find out number of such zeros previously, that will give me number of such subarrays, number of such good subarrays. How good? Such that their count mod m is actually equal to k. So I know number of such zeros previously are 1, 2, and also 3 of the very beginning. If you forgot, I have a 0 also for the very beginning, which ultimately shows one thing. You can take this entire sub array also. So now this count of 0 will show me that, hey Aryan, you can take this sub array, you can take this also as a sub array, and you can also take this also as a sub array. So for this particular index, all these 3 sub arrays are good. And how we got to know? By the count of such zeros. So you will maintain a map or an unordered map to maintain the count of your prefix of values, because it is nothing but a prefix sum, but with a mod m, logic. So you will just maintain the prefix sum mod m of the entire stuff, and then simply go and find for every I, go and find such prefix 1 mod m, which is actually, okay, for this I would know the current prefix of I mod m. I'll do a minus k because of this logic, minus k. I'll do a plus m mod m. I'll get some value which is a prefix of let's say j mod m. I want all such of the prefix of j mod m previously I have found before, which is nothing but finding the number of zeros I have found before. I'll simply say, okay, for this index, number of zeros found before were actually 3, which will say me I can just make 3 such a sub arrays ending that at index I, and that's how you can simply get this solved. That's the reason I just specifically went on from the back. See, again, it's actually a tricky question because it just, you will get confused in the mod and stuff. But I specifically went on from the start saying that go and firstly make sure focus on the one condition. Now when you have got all such good numbers, now the next condition is to find the count of such good numbers in a range or in a sub array. So how will you do it? By simply using a prefix sum. But now you want the modulo also. So count modulo. So again, for the prefix sum, just do a modulo. But now you want the count modulo to be equal to m. You can find the count modulo of any range, but now you want, okay, what all such ranges are there such that the count modulo m is actually k. So for that, okay, you are at index I. Now you want okay, earlier what you were saying, okay, for this index I, for this index j, now the count modulo m is k. Now out of what I am saying is, if you have index I, you want the count modulo m is k, just find all such j's previously. And that's how you can simply get this solved, by simply using this condition right here, and you can just simply transform it to get all such prefix of j's, which is previously then that of I, and get all such j's. For that, just maintain an unordered map to have the frequencies of all the numbers, so as to know that index, the number of such sub arrays ending at that index and for sure being good are actually 3. Cool. We actually simply implement this down. If you have understood the entire logic, can we please smash that like baby to 45 likes? That would be super great. Just 3 more, that would be super great. Cool. As we saw initially also, we have 1 0 right in the very beginning, and that is actually also counted, right? So I will just increment my, for 1 0, I'll just increment my 0. I'll go on from left to right. Again, I'll firstly make sure that that number is a good number. If that number is a good number, just simply increase my prefix, right? For sure. If that number is a good number, only then increase my prefix. And as you know that, okay, I'm just maintaining a prefix mod m also, because ultimately I will be iterating on the prefix mod m value and not the actual prefix value. Cool. I'll go on the prefix mod m value, and I'll go on. Now, I can only add, in my answer, I need to add all such good sub arrays. For that, I know, okay, the current prefix value is this because I am at this particular prefix. I am at this prefix, I am at this value I, so I am at this prefix value currently, and it's nothing but a prefix mod m value, which I have already found out, which is a prefix mod m value I have already found out. Now I know this, I'll do a prefix minus k plus m mod m to actually go and find, okay, prefix minus k mod plus m mod m to go and find all such previously values of prefixes. That's a count, and that's in our map itself. So I'll go and ask for my map to go and find all such previous value of prefixes to get the count of all the previous value of that prefixes for that particular prefix value. What's the count you have got previously, and simply add in my answer, because that is the number of sub arrays you get being at index I and having that prefix mod m as the current value of the prefix. Again, when this is done, which means, okay, your I at index is done, simply increase the prefix value, because you will actually have to maintain the count. So as my 2 is done, so I know I will go on next to this particular index, but for sure I will have to update my map also with the count of 2. So I'll just update, okay, for the map MP of prefix value which I've already found, increase it by plus, and that's how you can simply get this solved. You can also make the array, prefix array and stuff and then solve it down, but still a simple prefix variable can also get it done. For me, the more intuitive was making a prefix array and then visualizing and then solving it down the way I solved it, but it's a more lesser space solution, which is, it is not using any extra space at all, just a map is being used, that's it. While the solution which I made, it had a prefix array entirely, and then we were actually solving it to get, okay, I made the entire array, I made a prefix mod array, and then I just actually iterated on the prefix mod array to actually find the actual ultimate answer. But you know that, okay, you can just find the prefix mod in the same step itself, and you would not need any specific array for that. Cool. I hope that you guys got it. We'll quickly go into question number 4. Before that, we'll actually have a quick chat read. But before that, can we please smash that like baby to 45, like just 2 more? That would be super great. भैया एक टेस्ट केस 2 8 10 लेंथ का, दैट वाज अ टेस्ट केस ऑफ काफी बड़ी लेंथ का ना. दिस वन यू कैन हैव 1 2 3 4 5 6 7 8 9 length. That's good. Right. Cool. Create an array 1 if create an array 1 if nums of I modulo m is k. Find subarrays with k plus mod j plus 2 into mod 1. Once it can be one thing. Binary lifting पढ़ा दिया क्या? See, firstly, like binary lifting, Shubham, like I have already taught binary lifting in the previous lecture entirely. Although this binary lifting was much more in deep. For LCA, see, it was a two-way kind of binary lifting, which means you were actually lifting the weights also and also the nodes. In this, you'll only be lifting the nodes, but if you want, then I'll highly recommend, please go and understand the binary lifting from this lecture for sure. But we'll also explain binary lifting in this video also, but we'll not go in very deep of binary lifting because I have already explained binary lifting in one of the videos. Just write on YouTube binary lifting by Aryan Mittal, you will get the binary lifting video. But in short, like if you don't know, I'll just explain you what binary lifting is, why that is used, what is that, and all that stuff. But still, make sure that, okay, you must have watched this video. It's a very good application of binary lifting. Cool. Which question is about binary lifting and LCA? That's a 4th question. Awesome, bhai. Noah, hi. Didn't get it, but that's done. Binary lifting बढ़ा दिया गया. Thank you भैया. Thank you so much Ekansh. आपसे पढ़ के अच्छा लगता है भैया. Thank you so much Lucy. Cool. We quickly go on to question number 4th. Before that, can we please smash that like for sure? See, again, whenever I teach any concept, please make sure that at least you watch that video and make notes of it and understand the concept at least. That it should not be the case that if I have taught binary lifting previously, and that's a very recent contest, very recent, like just 6 days ago, which means the last contest, we understood binary lifting. If still you don't know binary lifting, which means, okay, you're missing the contest and you are not making notes and stuff. So please make sure that you at least study and at least should be knowing what it is and how you actually solve it and how it can be done and why it is useful at the first place. But we'll actually go on to it. It's pretty easy. This question was a bit harder in comparison to this one. It's a much straightforward, very easy question. So no worries on this part. But yeah, again, please study it after this video. Before starting, can we please smash it to 50 likes? That would be super great. Minimum edge weight equilibrium queries in a tree is just saying, okay, I have an undirected tree. Again, it's a tree with n nodes labeled from 0 to n minus 1. Right. I'm having an integer n, a 2D integer array edges of length n, n minus 1, which means a tree will have a number of edges as n minus 1, right? Right. Edges I have represented as u, v, and w, which means from u to v I have a weight w of that edge. Cool. Now I'm also having a queries of length m, Now every query is just saying, okay, it's a AIBI, which means two nodes of a tree. I just need to find out minimum number of operations required to make the weight of every edge on that path AI to BI equal, which means I will have AI BI as two nodes in my tree. I will have a path between them, and for sure it's a tree, so I will have a unique path between them. Now if it's a tree, I have a unique path between them. I would be knowing, okay, if I have a path, which means what all weights are there at the edges of that path, I want to make all of them equal. So for sure, if let's say I have I'm making just a one path, right? In general, I have the weight as, let's say, 1, 2, 3, 2, and 1. So one thing I can say, I will make all of them as 1. So I will make 1, 1, 1, right? So I will just have to do 3 deletions. Or I can say I will just make everything as 2 to 2. So I'll just make 2, 2, 2. Again, I have to do 3 deletions. I'll make everything as 3. I'll make it as 3, 3, 3, 3. I have to do 4 deletions, but I want minimum number, so I'll just do as deletion as 3. What if I just say I'll make everything as 4, 4, 4, 4? That's just a nonsense, because it's nonsense to make everything as any other number which is not even there. So I will never make it as 4, 4, 4. It's just a nonsense. So I will just use any of the existing numbers to make this entire path from A to B as same. So I will just do some number of deletions. So that is the quick crux of what the question is asking you. Again, first, just mark this words as Bible, right? Just mark this words that if you want to find the path, the distance, the nodes, the values, the edges between two nodes of a tree, and again, when I say two nodes, there are multiple queries and not only two nodes, which means I will be calling this M for many such queries. You will see my M is actually a lot, which is 2 into 1e4. So for this 2 into 1e4 queries, I can't go on this entire tree again and again, which means for this queries, I know I have to go on to every query. For sure, I'll go on to every query because I want to find the answer for every query. For every query, I can't go on in the entire tree between two nodes. I can't go on it. I will have to find a smarter, easier solution that I can find the path between two nodes of a tree. Again, my query is just saying, again, I'm saying, how to know that LCA or binary lifting is going to be applied is, again, I'm repeating that you are just given two nodes of a tree. You have to apply operation on these two nodes again and again. When you have to apply operation of two nodes of a tree again and again, just make sure that, okay, you should be able to access the path between them, or basically these nodes, you should be able to access very fast. Ultimately, you want, okay, if these two nodes are linked, so you should be able to find the path between them as fast as possible. Here comes the concept of LCA or binary lifting. What I mean by that, I'll show you, but it just will make sure. Let's say if I ask you, hey bro, if I want the path between 4 and 5, okay, that's a path between them. That's great. If I just ask you the path between this and this is nothing but this. Okay, the path between this and this, it's nothing but this. So you saw one thing. I want this stuff to be as fast as possible. Now, if it needs to be as fast as possible, so the fun thing for sure comes in my mind is, if I want to find the path between two nodes of a tree, can't I just do one thing? I can just assume one of the root nodes. I can find the root to that one child node and root to another child node. So that's a path. So for that, you got to know one thing, that the root is important. But I can also say the root can be this also. I can say the root from here to here and then from here to here. That's also true. But what is this root saying? Ultimately, the path between 6 and 7 is this path only. That's the shortest path. You can't just go here and then come back, and then that's also one of the paths. But yeah, I want the kind of a shortest path between 6 and 7. So one thing, what do you know about this node? What is this node? What is this node 3? This is called the LCA, or it is called the least or the lowest common ancestor. Lowest common ancestor. Just saying that 6 and 7, it is the common ancestor and is the lowest ancestor which is common between both of them. And that is what I want to actually get the path between 6 and 7. Again, one is also an ancestor, but it is not the lowest one, or it is also common for both of them. One is also common for both of them, but it's not the lowest one. I want the lowest common ancestor, right? Again, so Aryan, are you saying that for every node I need to know the lowest common ancestor? Yeah, ultimately you should be knowing it, but then Aryan, how would you find the weights? Or basically, I'm concerned about the weights, right? I'm concerned about the weights. I'm concerned about these weights 6, 8, 2. So how will you find the distinct weights in this particular path? You will have to go in the entire tree again. So it will be again O of n. No, for that I can just do a sum up pre-computation stuff. But for sure, right now, to just get the path between two nodes 6 and 7, I know one thing. I need to find the lowest common ancestor. So that's a separate problem altogether. We'll go on to it, how to solve it, but that is solved via binary lifting in the shortest possible time. Again, to find the lowest common ancestor, there are multiple ways, but the best algorithm is binary lifting, by which you can solve the lowest common ancestor. We'll see how, but is it the problem? Okay, finding the LCA was one part, but ultimately the concern was finding the weights 6, 8, 2. Ultimately the concern was finding the weights in this particular path. For that, I need to do some pre-computation. But pre-computation, I can only do it. Okay, I can find the LCA for any two nodes in, let's say, some very short time. And when I say very short, I actually mean if the height is actually, let's say I have n nodes, so I can find in log n time. That's the worst case. When I say I can have just a straight tree of n nodes, n, like this, I can find in log n time any LCA. But again, my concern was to find the weights. For the weights, I need to keep track of something. What? I can't go and start from here itself and say, okay, from 3, the weights are up till here are 6, and from here the weights are 8 and 2. Okay, so you can just get the weights from here, but get the weights from here. It can't done like that. So you have to just go and ask, okay, bro, up till 6, what all weights are there? Bro, up till 7, what all weights are there? Got it, bro. Got it. So I can just say and do a pre-computation from the root node. Now, for sure, a tree, I can assume a node as a root node. Okay, now this is a root node. Now, if this I assume as a root node, I can just easily go and as I go on from the root node itself, okay, I can go on from the root node itself. I'll go and say, as I'm going down, I'll say, okay, bro, from root node, you have 4 as the edges which you have got. Okay, bro. As I go on, I will pass in this values 4 and 4. Bro, you have got 4 earlier from the parent and you have got the 6 as new. Okay, cool. I've got 4 and 8 as the new values. Okay, cool. Now for this, I got the values of 4, 8 and 2 as I pass on. So basically, I am just passing on the number of different edges values to my actual child. Aryan, which means your tree is n size big, so you will pass on n values differently. No, that is a bit catch in this problem, that okay, you will see that the weights are only 26, which means I can, rather than passing the actual values 4 and 6, I can have a count as a kind of a map, and I can just pass this map entirely. I will have a map of size 26, which will actually store, okay, and it's a map for every node. For every node, I will have entirely map, just saying for this, the count of 4 is 1. So at 0, 1, 2, 3, 4, so 4 values 1. Okay, it will just say that for me, okay, sorry, here it is not 1 is here, 0, 1, sorry, 0, 1, 2, 3 and 4, count value is 1. Again, for this, it will just pass in this particular map entirely, and we'll say, bro, the count values actually again, for this 1 was there already, so 6 is actually again a 1. So with this, I can easily get to know. Again, just to showcase, I just showed you by using 4 and 6 just to know, but I can maintain it efficiently by using a map. And in the map, I know I only have 26 different values of weights, so for sure I can just increase the count in this map itself, or basically a kind of an array itself, to actually get to know, okay, what all such different values are there. Great. Now if I just ask you now, bro, can you just find the number of, like, what all values are there? And now when I say values, I will again just ask you that what all 6, 8, 2 are the actual values between the node 6 and 7. So now if I ask you the values between node 6 and 7, what are these? You can just go and say, bro, my LCA, I'll go and talk with my LCA, and he'll also go and talk with his LCA, right? Go and talk with the LCAs. Now, if I go and talk with the LCA, he'll go and talk with the LCA, he'll go and talk with the LCA. Now, he will have the values 4 and 6 as the values which he has. He has 4, 8 and 2. Is it 4, 6, 4 and 2 are the actual number of values between 6 and 7? No, it is not. Because 4 is counted twice. Why twice? Because of this 1, 6, because of this 1, 7. So 4 you saw was counted twice and was not even there in 6, 8 and 2. So to actually get the number of values, or to actually get these values 6, 8 and 4, 6, 8 and 2 between these nodes 6 and 7, I can just say it's nothing but whatsoever, let's say, name it as a node A, name it as a node B, name it as the LCA, and it is the root. So the count, or the, let's say, the Q is the count, or let's say the C is the count of values for node A, and for sure also for the node B, but subtracting twice the count for what? For the LCA. That will be the actual count. And when I say count, I will actually iterate for the entire map itself to get the entire value of the count. Because it is the number of distinct weights, it can only be 26. So actually everything I'm going on in the array form, like in the weights form entirely. So got to know one thing for sure. If anyhow I got to know about the LCA, I will actually maintain, what I will do is, anyway, let's say anyhow, if I got to know about the LCA, I'll for sure maintain a kind of a array of size 26. In that array, it will be nothing but a hash map kind of stuff, which will actually maintain, okay, for that particular 4, what is the count so far? I can actually keep on increasing that because the array size will remain same, and that will not impact my complexity. I will have it for 6 also. I will have it for this number also. And I can just have it a for loop where I will just iterate on all the numbers, 26 numbers. And with that, I can just find the actual new count, or basically the new hash map, saying for this path between A and B, what all count of weights are actually there. So that will be new hash map, which means I can just iterate this on all such weights, all such weights in my actual, let's say all such weights in all 26 weights. I can just iterate on that. It's a node, and I can just have a weight also, C W as a weight, W as a weight, and W as a weight. Just saying, okay, I will just iterate this value for all the weights, because I'm again saying I'm iterating on the weights as an hash map. So that is okay. One part of a problem is done kind of, that I know, okay, again, it's not an easy problem. The submissions are pretty less for it, but still, if you can just stay with me and just be motivated to solve it, you will be able to solve it. So right now we have just found out, okay, if anyhow I can get to know about the LCA, I can maintain a kind of an array of counts of weights from root. I'll have a root. I'll firstly pre-compute the count of weights from the root, where I will, from the root, I'll pass in the root kind of entire values to actually their child, and then I can just, if, okay, it's a new weight, so for the weight for the index 6, I can just increase the value by 1. So as to say, okay, the count of that weights has been increasing. Now when I want to find the distance between, or basically when I want to find the actual number of different weights in this entire range, which means in this entire path from 6 to 7, I can just go on and ask for all the weights up to 26, go and ask for 6, for 7, and also for the LCA, and that will be the entire logic. For A added, for B added, and for twice the LCA subtracted. Twice the LCA subtracted. And that's how you can simply get all the weights in this range from 6 to 7. Now let's say you have got the entire array in which at location 6, at location 2, and at location 8, I have 1, 1, 1. So ultimately in the end, just one fact remaining. Okay, you have got the ultimate number of weights, or basically you have got the all weights in a path between node A and B. Simply you want your main task is to make all of them equal. So now assuming, okay, I will make all of them equal as 2. So whatsoever is the count of remaining weights, just add them. If I want to make all the weights as equal to 6, just count the remaining weights, I will simply add them. If I want to make all of them equal to 8, what's the count of weights? Remaining weights, simply add them. And with this, you can simply get everything as solved. Now, everything is sorted so far. Now, the main concept is how to find the LCA. So now the main problem for you to solve this problem, solve it is actually solved. Now the only thing remaining is how to find the LCA. Right now, I'll just simply remove everything and I'll just show you how you can find the LCA in log n time, or it is the best efficient algorithm to actually find the LCA. Again, I'm saying the main problem to solve is actually done, which means if by any how you can get to know what is the LCA of any two nodes A and B, as I showed you, you will just maintain a kind of array which will actually maintain the count of all the edges which you are getting. For 4, I will just in my 4 I will increase the count by 1. For 6 I will actually pass the value of parent firstly for 4 by 1, and for 6 I will just simply add a 1. For 8 I will simply have a, and with this you can simply go and solve it. So this is actually solved. Now the concept was to actually how to find the LCA of two nodes. It's nothing but simply, again, as we have seen previously also, if you want, see what is a binary lifting. If you don't remember previously of the last video, and when I say last video, I actually mean this particular video contest. I actually explained pretty well, very deeply. But it's just to know the entire concept of binary lifting is just to make sure to access the parent. Let's say if it is a node U, or let's say if it is a node A, I want to access the eighth parent of node A. I want to access in the shortest possible time. So one way is sorry, let's say I want to access the sixth parent, or not even sixth. I want to access the sixth parent. If I want to access the sixth parent of node A, so one way is, okay, first parent, second parent, third parent, fourth parent, fifth parent, and sixth parent. One way is I go linearly, and if the size is n, which means the number of nodes is n, I am going linearly up to access the sixth parent. But binary lifting, with the help of binary lifting, I convert this number 6 to actually a number in the binary form, which is 1, 1, and 0, showing, okay, it is a 2 raised power 0, a 2 raised power 1, a 2 raised power 2. So just says is you can just hop on in the powers of 4, in the powers of 2, and can find the parent, which means for every node I will store their parents in the powers of 2. For this node A, I will store its parent in the powers of 2. When I say I is actually the power, right? I is actually the power, which means 2 raised power I is actually the power, right? So I'll just maintain it as, okay, 0 will say me, if I is 0, will say me I is actually this one, right? I is 1, I is 2. I as 0 will say me a 2 raised power 0, which is actually the first parent, which means the just immediate parent. A 2 raised power 1 will say me, and 1 is nothing but this. It is this, right? It is nothing but this. A 2 is in the power 4. So ultimately, I'm just saying, okay, I'll access the ith level or ith power parent in the shortest possible time, and I maintain only the ith power parent of every node. So for this node A, I'll maintain the ith power parent. For this node A, I'll maintain the ith power parent, okay, which means the 0th power parent, first power parent, power as in second parent, If the power is 2, I mean the fourth parent. If the power is 0, I mean the first parent. Cool. Now, if the power is 0, I mean the immediate first parent. Immediate first parent, you can for sure know, oh, that's your own parent. So that's okay. I can just maintain immediate parent, everyone knows. How everyone knows? Because if you're iterating on a tree from top to bottom, then tree, as in a tree you're iterating, right? You can go from a parent to child, right? So parent can always pass in my information to child. So while iterating the tree downwards, you can anyway, anyhow, just assign this value from parent of 0 to A. You can assign the value. Let's say it is as B, C, D, E, F, G, H, and I. Right. So it is for sure evident that while doing a simple DFS call, you can assign the immediate parent. Okay, that is a B. But ultimately, the prime concept of binary lifting is just to make sure that you are maintaining the levels of 2. You are maintaining the parents. If the folks are watching it, can we please smash that 50 likes? I know the folks have gone. Everyone is maybe for lunch and stuff, but I'm here with you. Can you please smash it to 50? Just one more. That was super great. Yeah, it feels very, you do such a kind of, I've seen like you guys, although like, I'll just put that bullshit in the end, but yeah, cool. That's emotional bullshit. Cool. Now it's just the prime concept. Okay, you are maintaining only the levels of 2. How? What you will do is you will simply get in from, again, I'm just giving you a high to a medium level overview. In very deep, I have explained in this video. I'm saying, okay, it was very deep. Now, how this will be helpful is you will only maintain the powers of 2. Now, when I will just ask you, you will just go and say, bro, I wanted, earlier I was going in at every parent again and again. Now I will go on to the fourth parent directly by just using this parent of 2, like level of 2 for A. Okay, for A, level of 2. Because I'm trying to find, and let's say if it is already pre-computed, it is already done, which means for at the level of 1, I have the value as C, and for the level of 2, I have the value as 1, 2, 3, 4, other value as, let's say it is already already pre-computed. If not, you don't know how to compute that, I'll also show that part also. But let's say if I've computed this value, so what will happen is, if I want to find the 6th parent, so I'll go and jump on the 4th parent. Okay, 4th parent I know, it's a E. 4th parent I will jump on directly, it's a E. 4th parent I'll jump on directly, it's a E. Now from the 4th parent I will jump on to the 2nd parent, that's a C. So sorry, for E I'll go on and jump for E, what is the 2nd parent. Again, for this also I will just maintain what is the first level parent, what is the second level parent, what is the third level parent, and so on and so forth, which means a 2 power 2. So for it, the immediate parent is F, for it the second parent is G, for this 4th parent is actually a I, right? So again, for this I will just go and ask for the first level parent, which means the first power parent. It will say me it is a G. It is a G. Cool. It is a G. It is a second level parent for him. It's a actually G. So again, for A, the 6th level parent was actually again a G. And that's how you can simply get this solved in log n time. You saw the hops were in log n because every time it's a power of 2, a factor of 2 which is being reduced. And that's how you can simply hop in the powers of 2 to actually get this solved. Again, now you know, okay, you will maintain only the powers of 2. But how you will actually, okay, the parent, immediate parent, you can actually easily solve it. But what about the other values, other parents? Will you be making it again and again? No, you will not. How you will make it? Simply saying, okay, if I want the second, it means a 2 power 1 power. Ultimately, if I can, something happened. If it ultimately means I want the second parent. I'll again break it down for you. Let's say if I want the first, second, third, fourth, I want the 4th parent. I can also say the same stuff as second parent and second parent, right? If I want the second parent, I can also say that as a first parent and first parent. So I just easily saying, okay, I can break my number 100, which is a number 4, in the binary form as two numbers 10 and 10, which is actually 2 and 2. I can break this number 10 as nothing but 1 and 1, which is actually nothing but 1 and 1. So it's nothing but breaking the number down into its smaller binary form. So I can know I want the second power. I want the second power. I want this one. And I always know the immediate parent of both of them because I'm iterating from top to bottom. So for top, I know the every values, what I want to have. So if I'm iterating the values for this, so I want the second parent itself. I want the second parent itself, right? I want the second. Let's erase this. I want the second parent itself, which is this parent. So again, I'll just go and ask what's the first parent, and for the first parent's value, what's the first parent? So it is nothing but parent. But I want the first, which means the 0th level parent. For what? For the new value which I got in, which is B. So how I got in? I got in by doing A's 0th parent, right? Which is nothing but B. It will just land off and place this value as a B. For B, I am again finding a 0th parent to get actually a C. And that's the final answer. And that's how it is actually very, very, very easy to compute everything in the binary form to get things done. Cool. That's the entire concept of binary lifting, that how you can actually make this parents array, or basically the ancestor array, or anything whatever you want to name it as. But it is how this array is made. And when this array is entirely made, you can just go and find any parent whatsoever in log n time. Now, it was the concept of binary lifting. Still, LCA is not yet done. How you will use binary lifting to find the LCA? Again, if I know that I have some ancestor like this, right? Cool. Now, again, in this, I want to know what is the LCA of A and B. Firstly, I need to go. For sure, I need to know the LCA of A and B. So one thing is that you keep on moving up. But if I move one step up, and again, I'm saying it can be a bigger tree, which means I just want to know the LCA, right? It is at depth, let's say 0, at depth 1, at depth 2, at depth 3, at depth 4, at depth 5. Now, if I want to know the LCA of A and B, so the one obvious thing is, okay, I am at this location right here, and at this location right here. So keep on moving up until you meet. But it is at depth 2, it is at depth 5. So firstly, if I keep on moving up until I meet, it means I should be at the same depth. So what I will do is LCS makes sure that, okay, firstly you should know what is the depth of both of them. So you know the depth of B is 2, the depth of A is 5. Firstly, bring both of them to the equal depth. How you can do it? Simply just, you know that, okay, the depth difference is actually a 3. The depth difference is actually a 3. So you want to reach to a depth which is actually a 2. Firstly, I know my depth, I will just do a simple DFS recursion, maintain the depth. I know what is the depth like. Now when I know what is the depth, I know what is the difference of the depth. The D difference of the depth is actually a 5 minus 2 is actually a 3. So I need to know whatsoever is having the more depth. Let's name it as A node. So please, firstly make sure that, okay, you make node A reach 3 steps up, which means just saying, okay, representing 3 in the binary form, which is 1 1. Again, one way to go 3 steps up is linearly going 1 2 and 3, but we would not do that. We will go in the binary form, basically in the form of binary lifting. As we are going on the parent, we'll go in the binary lifting form to go in shortest possible time possible. So I'll just go and do a jump of 2, do a jump of 1. Now I have reached my third. At the depth of 2 I have reached. Now both of them are at the same depth. Now when both of them are the same depth, now you can just keep on moving both of them simultaneously at the equal heights, and again, just as soon as it reaches the same parent for both of them, you are good to go. What I mean by that is, again, for this concept also, let's erase this and make another kind of a depth. Okay, let's have one more depth, and it goes in. Cool. So what will happen is, now again it is at the same level. Now I will just keep on moving both of them parallelly, equally, and as soon as both of these parents meet, his parent and his parent, if both of them meet, okay, I have got the common ancestor. That's the lowest or the shortest common ancestor. So now again, for them to go on, again I'll go on in the binary lifting form, which means I'll know, okay, I'll jump, I can jump, I can one thing I can try is doing a maximum jump of some XYZ. That's also possible. Else I can just do a simple jump. So I know, okay, I will just do a jump of firstly I'll do a jump until unless I'll get the same parent, and I keep on doing the jump until I have the different parent. So as you know that if my n is 1e5, the log n to the base 2 value is actually at max 20, 25, right? It's actually 20. Worst case, I am assuming. So in this example, I will take the n as 25. Sorry, log n value as 25. But still, it's at max 20. Just saying that you will actually move up log n to the base 2 steps, which actually at max 20 steps you can move up. So now I will just try moving both of them up. But now again, moving up is in the binary lifting form, and it should be, okay, it should have become the same parent. So if I just ask you, what is, let's say, I will just try from a very high value. I will just say as a 3. Now when I say a level 3, say a power 3, I actually mean 8 steps parent. Okay, 1, 2, 3, 4, 5, 6. Let's say a 7, 8. Okay, 1, 2, 3, 4, 5, 6 for sure. 1, 2, 3, 4, 5, 6, 7. Both are the parents same. Okay, cool. If the parent is same, don't move. I'll try for the level 2, which is actually, sorry, a power 2. Actually means the fourth parent. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Okay, still it's the same parent. So don't move at all. Let's try for level 1, which actually let's try for a power 1, which actually means the second parent. Okay, 1, 2, 1, 2. Oh, it's a different parent for both of them. Cool. Now if it's a different parent, move both of them up. Now both of them are at this location right here. Cool. Now I will try for the lesser power, which is actually power 0, which actually means the first parent. Oh, it's same. Cool. If it's same, okay, cool, it's a same parent, just stop down. I stop down, I will just know, okay, when I stop down, their immediate parent, whatsoever is there, is actually their lowest common ancestor. Because I was moving only my nodes only when their parents were different. I was only moving them up only when their parents were different. Now as soon as, and why I showed you this particular factor, why I showed you this 3, 2, 1, 0, which means 8, 4, 2, 1. Why I showed you this? Because I'll go on from the highest power of 2 to the lowest power to actually go on in the, highest steps first and then the lowest step. I'll keep on going and taking the lowest steps so as to find the LCA. When this is done, I would know, okay, at this point of time, I have tried to go up as much as I can by using the different parents. Now whatsoever parent is there, it will be the same parent for both of them. Now when the parent is same for both of them, I have found their ancestor, which is the lowest common ancestor for both of these nodes A and B. That's how you can simply get this solved. And again, finding the parent, that is done by binary lifting, which I explained here, right? It's just that the only concept of LCA in this part is that firstly, you have to maintain the depth of the nodes, which for sure you will just pre-compute that previously. Now, when you are done with this, ultimately, you will firstly make sure whatsoever node is at the more depth, just firstly bring it up till that a depth difference by using again binary lifting. When you have brought both of them up, now simply keep on moving both of them up in the powers of 2. Considering their parents are different, only then move them up. Okay, I am moving them up, I'm moving them up. Ultimately, if I have reached these two nodes where their parents are same, So one case it can be that okay, one case it can be that okay, it is the node itself, it's the parent itself, which means A and B are both the same. It can happen, but if not, then what I mean by that is it can happen that I'm going on B and it's A. So it can happen that I'm going on top. So rather than going in from here, A is actually the parent itself. So again, the ancestor for A and B is actually the lowest common ancestor for A and B is actually A itself. So if that is the case, we will have a simply if condition of if A and B have become same, simply return. But if not, ultimately I will just stop at this point where actually what will happen is now it has landed to a location where the parent of both of them is actually same. And if that is the case, that parent is actually the lowest common ancestor for both of them. And that's how we were able to find the LCA of A and B of two nodes in just log n time. So I can just simply go and find the LCA of A and B of two nodes in log n time. And for sure, to compute the depth, to compute the entire hash map stuff, which I showed you here, the tree which I made, where it's gone. Okay, it's somewhere gone, not sure where it is gone, but yeah, the entire hash map for every entire node to keep track of the weights, different weights, it has gone from the root. So that is also, I can just keep track and do the pre-computation of that part. So it's just a multiple kind of stuff which you will be using, pre-computation, you will be using LCA, you will be using binary lifting, all that stuff in this particular video to actually solve it. So the main crux to actually solve it, I showed you previously. Now, after that, I showed you binary lifting. After that, I showed you how to actually solve LCA by using binary lifting. Cool. We actually look at the code. Again, that's not an easy problem. And like it's easy. It's a mixture of a bit complex data structures, which means you will use binary lifting, you will use LCA, you will use hash maps and stuff. But yeah, that's ultimately what it is. Cool. Firstly, our main thing is that we will initialize multiple stuff. We'll initialize a graph. I know that I need to make a graph from node U to node V with weights W, right? So I'll just make a graph for that. Again, I'll just show you in the top also that how that graph, so that's a global variable. Instead of passing in all the recursive calls, we can have it a global variable. Now for depth, as I showed you for LCA, you would need to know the depth of both of the nodes A and B, so you will also maintain the depth. So you can just you can just complete this depth array if it was simple DFS calls. Again, that parent is nothing but, as I showed you, parent of level, like the power of 2 to the node itself, which is actually a node U. So that's for the LCA part. That's for the binary lifting part, which we will do. And ultimately, that's a queue, as I showed you, that I need to maintain for every node the entire hash map. Okay, for the node U. What is the hash map of the colors it has got so far from the root? So I will just maintain for the QWU, where U is the node itself and W is the weight. Now this weight is nothing but just representing, okay, that value in this entire stuff. If the 4 is 1, if the 2 is 1, just saying, okay, for the node U, that particular weight, let's say this 6, weight 4 has a value 1. For node U, the weight 2 has a value 1. For node U, the weight 0 has a value 3. So Q0U will give me a value 3. Q4U will give me a value 1. So this is just giving me, okay, for every node U, what is the entire hash map, which is the kind of a map of size 26, which I have made for me to keep the track of the weight count. That is for this queue, right? We have made. Now, again, the same variables we have initialized in the very top of our entire graph. Again, this max log is nothing but I have just defined, okay, if my n is 1e5, then actually my maximum log n value, which is actually log n to the base 2, is actually around 20-ish. So even if you add a 20 here, still it will work exactly fine. But yeah, you can have any higher value, it won't consider that much, because 25 is also not that big. Cool. And this is nothing but what we initialized in our actual main function down below. Right. Just a second. I will paste the solution link for your guys' reference. Because it can get a bit lengthy. Where to find my solution? More details. Okay, 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 okay. It's working, working, working. Okay. Okay, that is not yet completed. Why, I'm not sure. Just a second, I'm just pasting a solution right here for your reference, such that like so that you don't guys have to, you know, um have it done again and again. I don't understand where's my solution gone. It is not even here. Yeah, it is here. But it is not being submitted. Okay, yeah, it is now here. I'll just use this link and will paste it right here for your reference, and also I will paste it in the chat also, so that you can actually look at the code as well. Right, cool. Let's get this done and pin the message. Cool. Now, it's just start for your reference to actually go in, because it's a long code, so you can just get confused in this. So that's the reason I just specifically pinned it down. Cool. Now, when we have initialized all the variables, just at this time to actually build the entire graph for us. So actually, we'll get the node U, node V, and the weight W. For sure, we actually want to look only at the specific weights, as I showed you previously. Also, if I have a path having weights as 6, 1, 2, 1, and 6, there is, and if I don't even have 4 in my entire tree, so it's of no point to actually make the nodes as 4, 4, 4 itself. So whatsoever values I have, weights I have in my entire tree, I can just push them in my nodes. Even if, I'm saying, even if you don't push them in your nodes, even if you don't push this in your a vector or a set, sorry, even if you don't push that unique values, which means even if you try for the value 4, still you will get a higher value, which will not impact your answer, because you are keeping the answer as always minimum. So that's just extra for you to insert this in your, you can just make this as a W, as a new set, to just keep track, okay, what all weights you have in your actual tree, so that you just try only those weights for your answer. It's just extra, because you can also anytime iterate on just 26 weights again and again. That's very, very, very obvious, or very okay for you. Now, I will have a node U and node V, as simple as we push in a graph. For a U, I push in the V and W. For V, I push in a U and W. Now, when this is done, we'll actually build the entire graph. When I say build, I actually mean I want to build the parent array, which is actually showing parent I, U. I is nothing but the power of 2. For the node U, what all are the parents of that? I'll need to maintain the depth, for which I'll use a DFS function. I'll also need to maintain the Q, right? Q, which I showed you as previously also, where it is gone. Q, as I showed you here as well, right? I showed you Q for every node, for a specific weight, what is the weight count from root node. So that is also, I will just build in via the DFS calls. So that is, I will just complete doing the build function. Cool. Let's quickly jump on the build function. Again, for the build function, firstly, we have to initialize everything with -1. So I initialize my entire parent array with -1. Again, for this parent, it's nothing but parent of I and U. U is nothing but the node, which I can have n nodes, and I is nothing but a power of 2. And this power, it can be at max log times, right? And this log I have defined previously as well, at max size 25. So I just did initialize everything with -1, saying, okay, the parent is -1 initially. Although you will say, Aryan, but you were saying that initialize parent of 0 node U, you will initialize as you will do the DFS call. Yeah, I will initialize that when I will do a standard DFS call from the root node. When I will do a DFS call, I will just keep on giving the parent value to all the nodes. I'll show that part also. I'm done. But yeah, if the folks are watching in, can we please smash that like baby to 60, that would be super great. 60, just 3 more. That would be super great. Cool. Now, as you saw, I also need to have a depth. Initialize the same as -1. Now, as I showed you, I want to fill in my depth and also the immediate parent of my parent array. I'm not saying the all parents. I'm saying just the immediate parent I want to fill in. I'm doing this DFS to fill in the depth, to fill in the immediate parent, and also to fill in the array Q. As I showed you, Q is nothing but for every node U, what is the weight count from the root node. That's the reason I'm just doing the DFS from the root node itself. Root node can be anything. I just put it as 0 itself. Cool. Now I will just do the simple DFS call. Cool. Let's go on to simple DFS call. Firstly, as we are doing a simple DFS call, as we need to maintain the depth, so I'll just keep on updating the depth, and as I go into a child, I'll increase the depth by +1. Right? Cool. Parent, initially you saw, as I go on to my child, I'll pass in me as a parent. So I will get the parent value also for me. For the initial node, the parent is -1, but as I go on and do merge recursive calls, I'll keep on passing myself to my child as a parent. So it is my child, and I pass myself node as a parent, so it will come ultimately as a parent for the child. So my child can update his immediate parent. Again, it is a immediate parent, a 2⁻0, which is actually a first level parent for the node U. It's actually a P. Cool. My parent and depth are updated. Again, one thing is remaining, updating a Q. For the Q, I need to know that the entire hash map of size 26, right, or the weights whatsoever I had, I need to pass all the entire map to my child also. So if I'm at the node U, I have got this entire hash map for me. I'll pass this entire hash map to my child, and also the weight. Let's say the weight is the current weight for him as the node from U to V. The weight, I will have it in my V dot second. The node will be V dot first. So I need to also update this V dot second count in my new hash map of V, right? So I just do the same stuff. I'll go on to all the childs V, which means all the childs of my node U. Again, as I can, it's a graph. It's a kind of a graph I'm iterating on. So I can also go on the parent of U, but I can't go on the parent again back from U. So I just have a quick check. If the child which I'm thinking it's a child, if it's a parent, then simply continue. If not, then simply go on all the weights. Although again, as I showed you here, you can also iterate on all the 26 weights. That's also obvious and that's also okay. But if not, you can also count on and go on all the weights whatsoever is in your tree. That's a very small optimization that would not hamper you at all. Instead of this, you can go on all the 26 weights also. Cool. As I go on in this, I'll get the current weight. If it is actually equal to the weight I am thinking of, which is this weight, so for sure increase the count by 1 in my new. So I just increase the count by 1. Rest I am copying as it is from my parent. From my node U, I am copying as it is into my actual child, which is V dot first. I'm just copying as it is. As soon as if I'm got this particular edge node new, so okay, for that add extra 1. For that, rest all copy as it is for your child nodes. So now my child nodes, everything Q is found out, parent is found out, and depth is found out. Simply go on and do a simple recursive call to a child, passing on to the parent and increasing the depth by +1. Cool. Your depth, parent, immediate parent, and Q is found out. Now simply come back to your build function. You have got everything out. Simply now start doing a binary lifting. As I showed you previously, also in the binary lifting, you will go on all the nodes, but in the increasing levels. In the increasing levels of powers of 2. Now, as you are going on in this, you will just firstly see that the parent of what you're asking of is not -1. And as I showed you also, where is this gone? Yeah. Parent of 1A, it's nothing but just if it is a I, it's nothing but I minus 1, I minus 1. So parent of I of node U is nothing but parent of I minus 1 of what? Parent of I minus 1 of node U itself. And that's the same stuff which I have written down here. Parent of IU is nothing but parent of I minus 1 of the parent of I minus 1 node U itself, right? And that's how you can simply get the binary lifting done. And with this, you will have the binary level parents of every node U. Cool. Now, when this is done, your main part is to actually go and start querying, start doing the queries, because your binary lifting is done, which means you have got the depth, you have got the parents at binary levels, and you have also got the Q, which shows, okay, from root node what all the hash map for every weight count is there for every node. You have got all the three stuff. Now you can just are good to start with the queries itself. I'll go on the every query. I'll go and get the node U and V. But before that, I need to know the LCA of both node U and V to actually get the distinct number of count of weights between node U and V. So I'll just go and quickly query the LCA of node U and V. It will give me the node, which is the LCA node of node U and V. So I'll go and have in my LCA function. Again, as I showed you, LCA function will work as it is, as we discussed before. Firstly, we have the different depth, both of them. Firstly, we will have make both of them depths as same. And when their depth have made same, then we will actually go on equal wise to actually go on until their parents become equal. Cool. Firstly, as I can have node U and node V, right? So node U and node V. Now node U and node V. Again, just saying that that I will only like in this you're just assuming that okay, your node V should be the one which should be at the bottom, right? So because you will be actually increasing your node V as up. So you're assuming okay, your node V should be at the bottom so as to bring your node V up rather than node U. So just to not make yourself confused, it's just the fact that it's just a fact that you just have to go up. Cool. Now coming on back, that we just have to go upwards, so it's nothing but it will shift to a V. Just assuming okay, the one which is more deeper is a node V rather than a node U, right? It's a node V rather than a node U. So I'll just go and make whatsoever is the deeper node. If the depth of node U is big, so simply swap node U and V. Just assuming okay, node V will be the one which is actually will be a much deeper one. I'll get the actual depth difference between both of them, and I'll just keep on doing until I will get both of them as a same depth. Now I'll just keep on going in my actual. For node V, I'll keep on going in the parent until both of them have got the same depth. Now it can be a chance, it can be a fact that as I showed you previously also, it's a B, it's a A. Then if I just going on up, it can be a fact that A and B become equal, which means A was actually the ancestor of B itself. So I'll just have a quick check. If both of them have become same, which means U was ancestor of V, so simply return the U itself. Now when this is done, now it actually means that okay, now both of them are at the same levels. Now when both of them are at the same levels, just keep moving both of them up in the levels, in the powers of 2. So I'll just move up both of them in the powers of 2 only and only when the parents are not same. If the parents are not same, simply keep on moving them up, both of them. Keep them moving up. Ultimately, as I showed you in the example also, it will ultimately land onto one of the cases where it will land on okay, to here and here, where the parent will actually be their actual ancestor, because now the parent will actually become equal, and so it will land on to this value where just immediate parent will be their common ancestor for both of them. So I'll just get their immediate parent, and that will be common ancestor for both of them, and that will be the lowest common ancestor for both the nodes for U and V. Now when I have got the LCA of node U and V, I need to find what? I need to find the actual number of deletions which I need to do from node U to node LCA to node V. because it is the path from node U to V, right? So firstly, I just get the entire depth, which means the entire length, just saying, okay, what is the entire length or depth? That's not required. You can just initialize that with into max also. That's also more than sufficient. Just the main crux of this is number of deletions required. Now, maximum number of deletions required, it can be at max the number of edges, right? Number of edges between them. Now, number of edges between them, that will number of deletions required. It can just be said by the depth itself. Although you can also initialize this with intermax, and then you can just keep on updating this. That will also be more than sufficient. But the main part is you go on to all the weights. Considering right now, I will just put on the weight as 1, and I can just assume, okay, if the weight as 1 is the weight count, I know the entire length of this particular stuff is, let's say, 1, 2, 3, 4, 5, 6. The entire length is 6. I know the entire length. I can get to know by the depth itself. Okay, for you the depth was let's say I'm just getting the depth from the root node, right? From the root node I'm getting the depth. Cool. From the root node I'm getting the depth. Root node getting the depth as whatsoever. For this U, the root node from the root node, the depth is 6. For V, the root node, the depth is 6. For LCA, the whole depth is 3. So I can just easily know the distance between node U and V, and that's again a problem itself altogether. What is the distance between node U and V? So it is nothing but the length between node U and V is nothing but 6 itself, which is the depth of U, depth of V minus 2 into a depth of LCA of U and V, which I have found already. When I've got this number, I will just subtract the number of, which as I showed you previously also in this, if I have 1, 1 as the count, so I know, okay, for node U, for node V, what is the count of this one, and I just use those number of ones. Rest I will have to delete. I know the length is 6. I know the count of 1 is 2. So rest all I have to delete, which is the 4. 4 is the number of deletions required, and I want the number of deletions to be as minimum as possible. For this, the number ones, I can just quickly go and say for node U and node V, for that particular weight, what is the count of that? But I will just do a subtraction from the LCA to actually get the count of that particular weight from this LCA, and it will be 2 into just getting the same stuff as we have discussed in the very beginning of this particular example. Cool. Now with this, you can just simply get it solved and getting the result which is as minimum as possible, because you are trying on for all the weights and picking up only those weights. Rest of weights you are just deleting out. With this, for this particular node, or for the particular query I, you will get the minimum as the value and simply return the answer, which is the length as equal to the query size. Cool. That's pretty much it. The complexity is Q into log n. Q is for all the queries and log n for the LCA factor for all such queries of node U and V to find the LCA between them. Cool. That's pretty much it. I hope that you guys got it. Can we please smash that? I will end the stream soon in just 5 minutes. But before that, can we please smash that like baby to 65 likes. That was a pretty big problem. Understanding the entire logic, that how it is doing, why we need a hash map, what's the entire crux of using the weights, because the weights are 126. Then we learned about binary lifting. Then we learned about LCA. Then we actually got the code. The code is pinned for you. Thank you so much. I don't know why, but I never understand your solutions. Maybe we confuse people because you sometimes extend it too long. Also think it while solving rather than the prior thinking. And also think about it while solving rather than prior thinking. Oh, see, there are different ways for people to explain. I explain how I like, and that's the most. If you like someone else's explanation, you can go to that guy or person. I am not saying anything, but see, again, that needs much more context. You can break this problem down to 3 parts. If you don't know anything, then I told for the person who knows nothing, which means firstly, and when I complete a stuff, I just tell, okay, this is completed. When the logic was completed, I assumed you know LCA. Then I just told, okay, how you will get to know what's the answer like. Now, for the folks who don't know how to find the LCA, I just told, okay, now I will tell what's binary lifting. I told binary lifting entirely. And then I told, okay, how you can find the LCA. So there were three parts: solving this problem, understanding binary lifting, understanding LCA, and that's it. I understood it very clearly. Thank you so much, Abhay. Sorry. Just that was pretty much it. Thank you so much for watching. It clearly depends upon person to person. That's true. Cool. Thank you so much for watching. I'm a bit hungry. I'll go and eat. I have not eaten since morning. Cool. But yeah, before going, can you please smash that like baby to 65 likes? That would be super great. Because of explanation, it keeps me going. Thank you so much, Sniper. Cool. Cool. Bye bye. Thank you so much. Before going, can you please smash it to 65 likes? We had done all the 4 problems. Again, the submission is down here for your reference. It's a big code. So yeah, submission will be required. Cool. Bye bye. But I highly recommend, please try it by yourself, and please put that in your notes also, because it's a very good problem of understanding LCA and also binary lifting. And also, I highly recommend just go and watch this video also to understand binary lifting much more deeper, because it was entirely based on binary lifting only and no LCA part. Cool. Thank you so much. Bye bye. Bye. भाई मेरा तो लग गया यार, पानी नहीं है क्या मेरे पास. Bye bye.